looks like y'all are getting the general idea of feedback system models, and we're going to continue that discussion today. Before I do that, I want to make an administrative note. One of the first homeworks was asking you to derive some transfer functions, and I think one of them was a circuit problem. I don't remember the exact circuit. I think it was some sort of a T network. I'm going to draw something like this. The details kind of escape me. I think it was something like this, and you had to find something. And I had sketched out a solution, and a couple guys found some typos. There's a few places where I talk about some symbols. I use something like G1 or G2 or something like that, and I got the ones and twos backwards. I think the general idea of the approach is okay, but I got a couple of typos that I'm going to try to fix up this weekend. The two guys who came to my office and found that, raise your hand. Are you here? Okay, so it's those two guys at the back. You can get the details from them, and I'll try to correct it to everyone's satisfaction. If you find any other errors in homeworks, let me know. All right, any other questions, discussions, concerns? Let me make another comment. Monday, let's go to, oh, now I can't remember the room number. I think it's Shelby 11. Oh, I'm gonna have to send an email. I can't remember. I can go to the room, but I can't remember the address. 111 something something. It's a computer lab. Okay, I'm gonna go through and kind of review some of the concepts we talked about in this class, and we'll step through a little bit of MATLAB just to see how it works, and also we'll step forward a little bit with a few concepts to show you how MATLAB does that. We'll continue on. So Monday won't be in here. I'll try to remember to send out an email note and get that room number. It's just up the hill. Okay. All right. So another comment. I tend to write in cursive, but I tend to write a little bit fast because I'm talking while writing. So I do this. This is supposed to be letter S. Sometimes I'll write this way, but the problem is sometimes this looks like delta. I apologize, and sometimes this looks like 5. Okay, so and especially when I use this fat pen, which I think is easier to read, it might look like delta. So, like any communication, if you don't raise your hand and say, honey, did you mean to get 6 eggs or 6 whatever, that's going to create problems. So if you have any concerns about the writing, don't feel shy about asking for clarification, whether it's about notation or in your technical work. People use technical terms differently in different fields. All right. One of the things that always tickles me is when people tell me they're working in intelligent control, and I said, isn't that kind of a misnomer? Is there anything other than intelligent control? I mean, is it dumb control? But when you're talking to a business major, sometimes you got to clarify things. All right, let's talk a little bit about some. The first thing, and it's block diagram algebra. You remember the thing that we talked about is the idea of the Laplace transform. And with the Laplace transform, we had this idea that if we have a signal in time, we could transform it to another domain where the language is S domain, not delta S. And so this is the Laplace domain. And calculus operations, y dot, in time, become a multiply by S. And integration in time becomes a divide by S. That's the main thing. this is algebra on this side, and this is calculus. Okay, we're going to be using this type of notation throughout the semester. Okay, so I want to emphasize that we're going to be using algebra a lot when we're working with models using this so-called S operator. And one of the things that we will do is we can then manipulate or work with signals in using algebra when we're working in this domain. And so we're going to see these diagrams, and we're going to see basically what I will call fundamental operations. And they're going to look like algebra. Okay? And so if we see a picture that looks like this, where this is some sort of expression, this represents some sort of system, and that's its model, and its input could be x, and its output we'll call y. And the relationship between x, y, and g is we're going to say that y is equal to g of s times x of s. Okay, you can say g operates on x. This is the input, this is the output, g operates on it. This is a multiplication. And because multiplication is commutative, we could also say x of s times g of s. The order doesn't matter, we're just multiplying things out. This is both an advantage and a disadvantage. The advantage is whether you write it this way or this way, it's mathematically correct because we're just doing a algebra operation. The problem is, as names and variables start flying around, sometimes you scratch your head and you say, wait a minute, which one of these was a signal and which one of these was the system? And you might have to go back and say, oh, this was the system and this was the signal. Okay, so there can't be that confusion there because we're just freely swapping things around. There's probably less ambiguity about this particular operation. Okay. So we see this in some of our block diagrams. We have a summing point here. We're taking the difference between two numbers, and we use the algebra. E of s is equal to r of s minus y of s. So a lot of the diagrams we're going to use will use these basic blocks. The idea of a gain, the idea of adding and subtracting. So we call this thing block diagram algebra. Now, let's turn our attention to the most basic control system model. And you all have been sketching these out in your bios, which I have found interesting. So continue bringing those in. But the most basic model might look something like this. All the variables, they're all in variables in S, like so, okay? So the references are, this signal here is E, the error. A represents maybe the controller or the compensator. This may be the plant. This may be a sensor. They're all dynamic elements. This may be a sensor, say, with filtering. So you may be, for example, trying to filter a noisy signal with an RC network. And so it has dynamics. And so these are all transfer functions, and these are all signals, and we've named some of them. And so what I want to do is just talk about the model. If we were to try to find an equivalent model, so we want to find an equivalent model of, let me try to draw a dotted line like this. You notice that this system has got several blocks in it, and signals flowing around all over the place. And many times what we want is we want to know what is the behavior of the big box. with this as an input and that as an output. And what we can do is we can use block diagram algebra to write the equations for this. So for example, we can write equations. We could write an equation for E. We can say E of S is equal to R of S minus this signal here. Okay, that's the minus. And what is that signal? That signal is C of S times Y of S. Like so. Okay, so that would be an equation that represents this summing point right here. I'll give you a second to see if you can have any questions, absorb that, catch up and correct my handwriting. Any concerns? All right, and I might write another equation for the output Y. Say, what is Y? Y is the output of this box. So it looks like B is operating on something, and that something is operating on A, and that something is operating on E. So I could say this is maybe A times B, that function multiplied together of S, and then multiplying E of S. Feel free to give names to unnamed lines, signals. Give that signal name if you want. Create an equation that describes that signal in terms of the blocks and other signals. But there's a lot of ways to create algebraic descriptions of this. Okay. But now these are all algebraic equations, and what we can do is we can now do some algebra operations to find the relationship between this input and that output. And so what we can do is manipulate the algebra to find the transfer function of that box. And the transfer function of that box should be, remember, transfer function always describes output over input. It's kind of like a gain. What is the gain of this big purple box? I'll leave that to you as a between class exercise, or do it at Chick-fil-A while you're eating lunch. Okay, you all do know Chick-fil-A is closing end of the month, right? Which one? This one out here. So go get your sandwich quick. I heard it's going to close for 2 years while they're building another building out there. So you see some buildings out across the street being torn down and stuff like that. So there's going to be a new building. I heard Chick-fil-A is going to be in the basement or in the bottom floor. My grandson's going to be disappointed, but it's one of his favorite places to go. We sit on the porch and watch the girls go by. He's only 4. But he's really cute. He's got this blonde curly hair. People always wonder if I'm really supposed to be with him, or am I some sort of pedophile or something who's got this little boy. He likes to, one of the things I shouldn't have done is I told him the definition of a Philistine. Y'all remember what is a Philistine from the Bible? Who is the most famous Philistine? Goliath, right? Bad guy, right? So I taught him when he was a little kid, about 2 or 3. I said, "You see that car not parked in the lines? Philistine." So we watched the people come into Chick-fil-A, and he says, "Grandpa, there's a Philistine." I said, "Yep." So we enjoy Chick-fil-A. I hope you will too. Take a little bit of time and go try to work this exercise. Try to find the ratio of y over r. I'm going to go ahead and give you the answer right now, and then we're going to do some examples of a little bit more complicated ones. Okay, so the answer, if we were to generalize it, draw again the block diagram, kind of like so. Okay, just draw yourself a little sketch of something out here. The answer, let's suppose this is the output, this is y and this is r. y over r. The theory is it is what we call the forward gain divided by 1 minus the loop gain. Okay, so I'm going to talk a little bit about what is forward gain and loop gain. One of the things that we want to take away from this class is that if we use feedback, we're going to change the behavior of the system. This was the original system. This was the process, maybe. Or let's go back to the previous diagram. This was the process. This is the thing that we're interested in making behave the way we want it to behave. It could be our dog. It could be our children. It could be something that we build. This is the controller. This is maybe something that's sensing the system. But when we put it in a feedback configuration, the behavior is going to be different. The system behavior won't be B, it won't be A, it won't be C. It'll be a combination A, B, and C. And the behavior will change. And we're going to describe that behavior. We're going to call it the closed loop model. We're going to basically replace everything by this dotted line. And the simplest systems can be described as forward gain divided by 1 minus loop gain. This is a special case of a more general problem. You know, you could draw a more complicated system that has loops, interlocking, all kinds of things, and there are equations for that. But they all come back to a basic idea is that feedback changes the world, and we hope that we're changing it for the good and not necessarily for the bad. And so we have this idea of forward gain divided by 1 minus the loop gain. So let me first talk about what is the forward gain. I think we may have enough colors up here to try to show what it is. This is the input, this is the output. This is the input to the big box. Okay, the big box. Put the big box dot 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 around it like this. Okay. Every block has its input, like this was an input. And this is an input to this box. And the arrow here is the input to this box. But here I'm talking about the input to the system. We can call it the reference. Okay. So when somebody says input, you say input to what? And they'll have to clarify. And here I'm clarifying and saying it's the input to the purple thing. And now each box also has its output. This is an output of this box. This is an output of this box. This little thing right here is the output of the summing point. But here, in the context of a closed loop model, Y is the output of this kind of purple box. So we'll call this the output. What we're deriving here is the so-called closed loop model. The closed loop transfer function, dot dot. Okay. Forward gain is what we do is we are going to just follow the signal path in a forward direction, follow the arrows. Okay, so going this way with my finger is not forward. Okay, it seems forward because I'm moving from left to right and I'm reading in English, and this looks like I'm moving from left to right. That's how we read, but that's not forward. The block diagram's implication is that the signal goes here, gets processed, produces a new signal. So this we follow the arrows. Okay. Now, what is forward path? Forward path means, let me kind of highlight forward path, or the forward gain is the gain between the input and the output. So you put your finger here and the other finger here, and ask yourself, how do I get from here to there, following the arrows? Okay. So you say, I gotta go from here to here, and you say, I'll do this. That's not forward. That's going backwards against the flow. This is forward. Okay, so forward gain in this case I'm going to highlight is kind of this path right here. Okay. Now loop gain is going to be, you see a loop here, and so what we do is we start anywhere in the loop, anywhere. Put your finger somewhere in the loop and ask yourself, what are all the gains that I get? I multiply them all up as I go around the loop one time. Okay. So I can start here, go all the way around the loop, picking up that gain. This gain is gain of 1, maybe it has a minus sign. This is a gain, this is a gain. Multiply them all together, I get back here. I've gone around the loop one time, that's the loop gain. Okay. Forward gain is picking up all the gains, multiply them all together like this. So loop gain is, this is the loop gain. This is the loop. Okay, let's do some examples. I want to emphasize these concepts only are valid in transform domain. Okay, if somebody gives you a time domain description, it doesn't work. We're doing everything with algebra, and algebra is correct in the transform domain. So for now, I'm going to try to remember to write everything in S. Okay? If you're in communication theory, you're probably using the Fourier transform. But it's still a transform, and everything applies without any problem. Okay, so this is a diagram. It's a little bit more complicated than the basic signal thing. A simple loop, because I've got some additional signals here. Let's give this signal here a name. Let's call it the reference behavior. We'll call this signal the output Y. Maybe we'll call this a signal that's working against us. Okay. This is my child, whose behavior I'm trying to make conform to the mores of the world. This is me. Okay? And I'm trying to do something positive in this child's life. This is a disturbance. I usually think of disturbances as not good, so I'll put a minus. That might be my rationale for putting a minus sign. It may not be the case. Okay. That disturbance could represent too much TV. I watch my kid, but the information I get about my kid is sometimes noisy. So this might be noise. Noise comes into the system, and so the information I get about my kid.
Are those both supposed to be plus?
Yeah. So the question is, are these both supposed to be plus? Yeah. Nothing sacred about these signs. But for the purposes of the example, make sure you get the signs the same as me, because it will affect the answer. Okay, so you do need to be careful of signs. Okay, there's nothing sacred about making this plus and this minus. You may be creating the model of your system, and you had decided that this is the minus and that's the plus, or maybe you decide that's the plus and this is a minus. But for the sake of this example, let's make sure that we get the plus and minus signs consistent with what's shown on the screen, so that your answer will be consistent. Does that answer your question?
Somewhat, yeah.
Okay. I mean, you could say, does noise have to be, is noise a positive thing?
The reason I ask is because they're both plus.
Yeah.
And I've never seen something like two positive terminals. Or
Yeah.
I might be thinking this too hardware specific.
Yeah, so you might think, I've never seen a battery with two positive terminals, but this isn't a battery. It's represent the summing of two signals, two things added together.
Oh, okay, so it's not a plus minus.
It's not a plus minus like a battery. It's a summing point. So these are summing points.
Gotcha.
Okay. It's a piece of information and another piece of information, creating this piece of information. Okay, so what we can do is we can find now some different transfer functions. Let's first find the transfer function between output Y and input R. Okay, I want to find the transfer function between input R and output Y. Here's the output Y, here's the input R. There's a lot of inputs into the system. I can think of R as coming in. It's a reference input. D is an input. It's a disturbance input. N is an input. It's a noisy input. Lots of inputs. Lots of outputs that might be of interest to us. I'm going to label this one E for error. Okay, let's find the relationship between R as an input and Y as an output. So I had to do a forward gain from R to Y. So I start here and I move my finger along this thing until I get to the output. Okay, and I just go make sure I pick up all the paths one time. So I see I have F, that's a positive, that's a +1, positive. So doesn't change anything. That's an A, and there's another gain, but the gain is just a +1. And here's a B. So the answer is F, A, B, that function of S. That's the forward gain from R to Y. And now what we want to do is we want to do the loop gain. The loop gain is 1 minus, and we want to start anywhere in the loop and go all the way around one time and pick up all the gains. Okay? So let's just start right here. Go once around the loop and pick up all the gains. So I see I got a minus sign, I got an A, plus sign doesn't change any signs, I got a B, keep on going around, I got a plus sign, that doesn't change the sign of the information, and then I got a C. Okay, so the answer is F, A, B, a function of S divided by 1 plus A, B, C of S. That's the new model. That's the model if I want to say, here's a system under my hands, the input is R and the output is Y, what's the model underneath it? It's FAB divided by 1 plus ABC. Okay, let's do another model. Let's suppose I want to know, I'm design this control system. Maybe this is my car. This is the speed. I'm measuring it with a tachometer. This is the cruise control. This is the desired speed. Maybe I have a filter. Yes, question.
So for creating that equation, you just ignore that in of S?
Okay, so the question is, what happened to N and D here? Okay, so the formula is, let me go back to the previous slides. We're picking up gains, or gains and loop gains. And so this is important. We're picking up items that are gains. And N and D are signals, they're not gains. Okay. Think about it this way. Think about when we do circuit analysis. I gave you a circuit, it's got 2 voltage sources, and you want to analyze it. What do you do to analyze something with two sources? You apply, superposition, right? You kill one source, analyze the circuit behavior under one source, then kill the second source, you analyze the behavior for the second source, then add the results together. And so that we're doing the same thing here. We think of this as an input. We want to know what is the output relationship to that one input. Yeah, there are other inputs. N is an input, D is an input. We're ignoring them because they're inputs, they're not gains. Okay, good question. Common error. Common error. Somebody will say, oh, D's there, but D's not on the path either. See, I'm going from forward gain from here to there. As I go here, I don't pick up D. And as I go around the loop, you know, N comes into the loop, but it's not, as my finger moves along, I don't pick it up. And it's not a gain either, it's a signal. Okay, let's do another example. Maybe that'll help clarify things a little bit. Okay, we want to find the forward gain from R to E. Forward gain from R to E. R to E. So, go from here, and that's the output. And so the answer is I get F. And then I do 1 minus the loop gain. Okay, so start anywhere. You go once around the loop. C minus C, A times C, A times B times C, and I'm back. And so negative a times b times c of s. And so the answer is f of time, the function of s divided by 1 plus a b c of s. Maybe I'm interested in how much error is due to the noise. Okay, so that might be a reason for wanting to know the transfer function between n, the noise, and this. How's my control system working? Is it a good control system? Well, I see there's a little bit of error. I didn't get the output to go where I wanted it to go. There's a little bit of error. But how much of that is due to my controller design, or how much of that is due to the disturbance effects? In this particular case, I'm saying, well, how does noise affect the error of the control system? So let's derive that transfer function. It's also a closed loop model. We want to find the forward gain from n to e. And I get this. Okay? But I'm having to talk and write at the same time with a pen that puts out fumes, so do not be shy about questioning whether I've got everything up there correctly. It's one of those technical skills you need to learn in this modern world, is delivering something, talking while walking, or chewing gum while walking. Some of us aren't naturally gifted in that area, so don't be shy about asking, wait, did you mean something else? Okay, we've had some questions come up about, what about plus signs, what about minus signs? We've had questions about, what about these other signals? Are there any more concerns about those? Do you see what's happening with these plus signs and minus signs? Okay. What would happen if this was a minus sign? How would my answer there change? Okay, because I got a negative canceling a negative. Okay. How would this answer change if this sign was changed to a minus sign? No, I don't understand, or yeah, it doesn't change the forward gain. Okay.
You have the 1 minus some function bottom, that would probably
Yeah.
have 1
Okay.
plus.
So y'all are getting it. You're talking about the bottom. Yeah, the bottom would change. But for this particular problem, again, the loop gain is going to be minus a b c of s, and I'll leave it there. Alrighty. All right. So we talked about several things today. We've talked about the idea of block diagram algebra and the feedback system model. The feedback system model, we want to walk away with this idea of forward gain divided by 1 minus the loop gain. We want to practice that a little bit. And then the last topic I want to talk about today is stability. Okay. This is a system whose input is u, the output I'm going to call y, and it has a model g of s. Okay? And so let's suppose g of s is some model. We derived it as a transfer function. It turns out to be, say, 3s plus 2 over 4s plus 5, like so. Okay? And what we're saying is the system stable? What does it mean stable? Stable is the engineer's way of saying, does this thing behave nicely? Okay, is the system behave nicely? Does it have nice behavior? And in particular, what we're typically interested in is we have a theorem out of linear systems. It says the system bounded input, bounded output, stable, if and only if G of S has no poles in the right half plane. Okay, that's a mouthful. So let me kind of pick it apart with this example and what that means. Okay, so we're saying the thing that we're interested in studying behaves nicely, it's stable. Well, what kind of stability? Bounded input, bounded output. Because our models describe just the relationship between an input and an output. Remember, when we derive transfer functions, there are some things that we ignore. We ignore initial conditions. Okay. Hey, you say, hey, there's a disturbance in our system. It comes in. Well, I'm ignoring that input. I'm looking at the relationship between input and output. Okay. All right. So we want to know, by looking at this equation, can I tell whether or not the system is going to be stable? Well, it says, well, I can test something. Okay, I can test something, and that something is this equation right here. And if that equation is satisfied, then I can say it's going to be a stable system. It will behave nicely. By the same token, if I test it and I discover the conditions fail, then I can conclude that the system is going to behave badly. Now, what is the mathematical test? I have to take a look at G, and I have to look at what are known as the poles. Okay, so what are the poles? The poles are the roots of the denominator. Focus. Roots of this equation. So I had to be able to solve 4s plus 5 is equal to 0. I have to solve that equation. Let me write that again. The roots of the denominator, 4s plus 5 is equal to 0. Later on in the semester, we're going to talk about the roots of the numerator. They got a different name. They're called zeros. Okay, roots of the denominator are called poles. So in this case, I need to do a little bit of algebra. Again, so I get s is equal to minus 5 over 4. Okay. Now, s in general is a complex number. In this particular example, it's just a real number. But in the most general problems that we're going to look at, s can be a complex number. So if I could sketch it in a plane, and this is what I'm going to call the s plane. S in general is something like sigma plus j omega. It has both a real and imaginary parts. RE means real, M means imaginary. And so I'll put the real part here and the imaginary part here. This particular number is minus 5 over 4. Minus 5 over 4 would plot right here. Minus 1.2 is minus 1.25. Minus 5 over 4. Did I do that right? Fraction is minus 1.25. Yeah. Okay, and so it does not lie. What is this idea of a right half plane? This is this. This is the, don't go there. If we have poles in the right half plane, the system is unstable. So in our particular example, this system would be considered a stable system. Now, you're probably curious to say, wait a minute, we determined this just by looking at this? Yes. The denominator fully characterizes the stability of the system, the fundamental behavior, the fundamental nature of the system. You say, wait a minute, you're ignoring part of the model. Well, that part of the model, the numerator of the model, does affect the behavior, but it doesn't determine whether or not the system is going to blow up or not. It doesn't tell you whether or not the system's going to blow up. Whether the system blows up or settles down is all determined by this. This will affect the response of the system. Okay. Remember when we did differential equations? Let me do a recall. if I wrote an equation like x dot is equal to minus ax, and the initial condition says x of 0 is equal to x0, okay? We know the solution from calculus is that x of t is some constant, a constant, times e to the minus at. Okay. This part, whether or not the function blows up, this is for t greater than 0, whether or not it blows up or decays is determined by this number here. The model for this system is going to be something like 1 over s plus a. It's in this part. Now what about this constant? Well, that depends on things here. Okay. So yes, the numerator affects the response, it scales it, but whether or not the system blows up or not, it depends just on the denominator. Okay. I don't want to go too far into this because this is going down calculus, and we're trying to avoid calculus, but I just want to try to tie it to something that you've seen before, in class before. Okay, let's try to do a couple examples. So is this model stable?
Yeah.
Okay. Don't be fooled by the minus sign. Okay, where do I need to put my attention? I need to focus my attention here. Okay, I need to solve for the roots of that equation. Okay, so I need to solve for the roots of s squared plus 3s plus 2 equal to 0. There are a lot of ways to do this. MATLAB can solve it. You can use the roots command and put in, what are the roots. We'll do that a little bit on Monday. I said we're going to go to Shelby, remember? All right, we won't be here. Unfortunately, you won't have a computer with you in here when you take exam 1 or exam 2 or whatever. You need some tool. So you're either going to be an old coot like me and can do a lot of algebra in his head, because I don't have a dating life anymore, so I sit around on weekends and do algebra. My dad died of brain cancer back in 2010, and I was going through his stuff on his desk, and he knew something was wrong with his mind. And he had all these little bits of paper, and he was writing things like sine A plus B is equal to, what is sine A plus B? Sine A, sine B plus or minus cosine A cosine B?
That, yeah.
Yeah, that, right. My dad was, yeah, right. He was trying to say, my mind's going, I gotta keep on exercising these things. So, some of us will be able to do this in our head. Okay. What tool might do this in our head? Quadratic formula, right? Anybody here know the quadratic formula song? Raise your hand.
What now?
There's a quadratic formula song. Anybody here a singer can sing the quadratic formula song? No singers in here?
Do it.
Yeah, okay. I heard somebody mutter calculator. Okay, pull out your TI-89.
Time out. You brought up the song. You gotta sing it now.
No, I can't. I told you at the beginning of the first class, what did I say? Can I sing or not? I cannot sing.
No, you did, but that doesn't stop you.
So, pull out your TI-89 or whatever it is, figure out what function solves roots. Make sure, I'm told the TI-89 will solve for roots both in complex roots and root roots. Make sure you put it in complex mode, because most of the polynomials that we deal with could potentially have complex roots. So, one thing you guys figure out this weekend is pull out your TI-89 and how do I solve for the roots of this thing. Okay? I'll leave you with this and then we're gonna quit. Last example. Same question worded two different ways. Is this system stable? Is y over r stable? Okay, so take kind of review these things and answer this question. Okay, so this example is a little different than the previous four. Okay. What time have you got?
9:47.
All right, it's Friday. Let's go to Chick-fil-A before closing.